Okay, so we're going to do a problem called tailgating. All right. So what is it? You're driving and you have a nice car in front of you at some distance, and all of a sudden he brakes. He slows down and stops. Now you see it, but you have a reaction time from the instant you see until the instant you apply your brakes. You have a time that passes, right? A small reaction time, okay? That is why, for example, they say that if someone is on certain medications, he shouldn't drive, because the reaction time can be very big, and that's not a good case, right? So what we have is we have the car being in front of you, and when the problem starts, okay, the front car is at some distance, it has some initial distance from you, its initial position is here, starts applying its brake, and of course it will do some distance before it stops. Now you, starting let's say from here, just because you have some time reaction before you see it, but you don't apply the brakes yet, so your motion is still constant, uniform. Now as soon as you apply the brakes, you will start slowing down too. Now the idea is, are you going to hit the front car or not? Okay, that means, will your final position be before or after his final position? Because I drew it separately, but actually you're on the same lane, right? So the idea is to find the final positions of both of you. So I have some values here. So let's say that the front car has an initial velocity of 24 meters per second. And when he starts, he's 15 meters in front of you. So if this is the zero position, he starts from 15 meters. So he applies the brakes. So he has some acceleration that I consider to be 8 meters per second squared. Now you started from position 0, and for some time, 0.7 seconds, you don't react. So your reaction time, I will call it reaction time, which is 0.4 second. You move with a constant velocity, which is 20. Okay, so he was going with 24, you were going with 20, you were relaxed, he was going faster, like, come on. That is why your reaction time is high. 0.7 is high. Usually reaction time is 0.4 to 0.6. Okay, I may have a little bigger, like longer. All right, so at that time you do a uniform motion for some distance, and then you start slowing down, and let's say that your acceleration, deceleration, right, is 10 meters per second squared. Let's have the negative sign in his acceleration too, so we know that he slows down. All right, so we want to know what will happen. I will see the two objects separately. I will use black for the front car. So what is his final position? All right. Okay, so I don't have time in his case, and I don't care for time in his case. I only care for how far he will go. So I think I can use the no time equation, saying final velocity minus initial velocity equals 2 times the acceleration over final minus initial position. Okay, this is for the front car. I start for the front car. I do know that I want him to stop, so his final velocity should be 0. I also know what his initial velocity is, 24, right? 24 meters per second squared equals 2 times the acceleration, which is negative 8 meters per second squared. All right? The final position, this is what I'm looking for, minus the initial position. So he started 15 meters ahead of you, so that's his initial position. That's what I have, right? So let's see. 24 squared, I should know 24 squared is 576. So negative 576, I use the units. You don't need to have the units. I just do it so you see. You don't need to use them. You can just add the correct unit at the end. I will prove that it will be at the end the correct unit. Okay, so negative 576 equals negative 16 meters per second squared, x1 minus 15 meters. Right, so I can get rid of the second squared, I can get rid of the meters, I can get rid of the negative sign, and of course I can divide 576 over 16 equals x1 minus 15 meters. And I forgot that there's a meter here. I think I should write it again. Right? So 576 meters over 16 equals x1 minus 15 meters. Right? 576 divided by 16, hopefully it will be a nice number. Divided by 16, it should be 36. So 36 equals meters, come on, equals x1 minus 15. So x1 will be 36 plus 15 meters. So it should be 51 meters. So this is where he stops. So he stops at position 51 meters. And I did find the correct unit. All right. Now let's go to you. So you do two motions for some time, which matters now. You do a uniform motion, right? And then let's erase it. And then you will slow down too. All right. So from here to here, you have a constant velocity for some time. So if I use the full formula, from 0 to x1, right? U from position 0 to x1, and this is what you're looking for, x1. Okay, if you use this equation, you do see that your initial position is 0. You have no acceleration. So what you find is that x1 equals the initial velocity, which is 20 meters per second times 0.7 seconds. And this is 14 meters. So you already did 14 meters to slow down. Sorry, you did 14 meters without slowing down. Now you start slowing down, right? Okay, so now I can use actually the no equation formula. Why? Because I don't have time, I don't care for time. I can use the other one, that's fine. What do I know? I know that I want my final velocity to be 0. My initial velocity was 20 meters per second equals to, my acceleration was negative 10 meters per second squared. This starts when my initial position is 14 meters, sorry. And I'm looking for the final position. Okay, so what do I have? Let's get rid of the unit. You know what it is. So it's negative 400 equals negative 20. That's a 20. X minus 14. So getting rid of this and dividing with a 20. So we find that 20 equals x minus 14. So your final position, the 2, will be at 34 meters, right? So you're going to stop. So this was at 14, and this is at 34 meters. So we see that you stopped on time, okay? He stopped at position 51 from the original, while you stopped at position 34. So you stopped way ahead. You're safe, okay? That's my driving. That's it. That's the tailgating. We can do graphs. Can we do graphs? Can we show how this can be seen in graphs? I didn't want that, but that's fine. Let's hope that I have a lot of time. So if I do, no, I don't have time. I have to stop. I have to show it in another time.